Hello, today we're going to look at a mechanical principles problem which is to do with fastenings in single shear. I've got a lap joint, so if you think of both my hands, this is one plate, this is the other plate, and I've got a joint, they overlap, and then the pen, okay, that's a rivet, and that rivet is going to try and stop movement in either direction between both the plates. Okay, and that's called shear. That's when it's loaded in shear. And it's like that because you've got a shearing force which is trying to cut the rivet. And we're going to find out how many rivets we need to hold our lap joint in place. So the question, a lap joint is required to join plates using rivets of 6mm diameter. The shearing force to be carried by the joint is 12 kilonewtons, so there'll be 12 kilonewtons trying to pull these two plates apart. And the shear strength of the rivet material is 300 megapascals. So just very quickly, if you look at this graph I've got here, I've got applied stress, tau, gamma, which is a deformation in the material. As we apply stress, the deformation and stress applied are they're a straight line, so we've got proportionality, and then we reach this point which is the proportional limit, and that's when we come out of the point where the applied stress and strain are proportional to each other. And we find that for less applied stress we get more deformation until we reach the point here. This is the peak of the graph, that's the shear strength of the material, and the shear strength of this material is 300 megapascals or 300 million pascals. Once we've gone past the shear strength of the material, you get to a point where eventually it's going to fracture. So this is actually the ultimate point in the material that we can rely on, whereby we know it's not going to fracture before that point. So that's the point that we use. In this case it's 300 megapascals, and a factor of safety is 8 is applied. Find the number of rivets required for the joint. So the shear strength of the material is 300 megapascals. So in order to apply a factor of safety, what a factor of safety effectively is it's a multiplier whereby if we find the ultimate point at which our system is going to fail, we then say, okay, we'll engineer it to a point where it would need X amount of times that in order to fail. So in this case we've said 8 times greater than the maximum expected load to be applied to that system. In engineering I can't remember ever seeing a factor of safety less than 3 applied in any particular problem. So when we take the shear strength, we get the shear stress, the shear strength here, 300 divided by 8, and that gives us 37.5 megapascals. Okay, so we can also say that the shear stress here is going to be equal to the force divided by the area, and the area is simply the number of rivets, the cross-sectional area of the number of rivets, and we can find that using this little formula. Area is equal to the number of rivets, that's n, times pi times d squared, that's a diameter squared, divided by 4. Now the reason we use this is because we're given the diameter of the rivets. You can work it out using the radius as well, pi r squared, but it's just as easy to use this. Then we have the shear stress is equal to the force divided by the area, and when we can then substitute this for A here, and then rearrange it so that the 4 goes at the top. So we get 4F, okay, and we should have tau in here because I've missed a step out here. So if we've got tau there, ooh, come on tau. Shear stress is equal to force divided by area. Substitute area for this equation here, and then take the 4 over to the top, and we end up with 4F divided by tau times pi times d squared would give us the number of rivets, that's what we're after, required for this system. And just to quickly prove that, if for example 8 is equal to 16 divided by 8 over 4, okay, then 8 is also equal to 4 times, take the 4 up to the top, 4 times 16 divided by 8. That, you do that with any set of fractions, you can work it out for yourself. You'll see that whenever you've got tiered fractions like this, the bottom one, the third one, so we've got the 3 layers, 1, 2, 3 layers, the third layer can always go up and multiply the top, so on and so forth. Okay, so what we end up with is this: the number of rivets required is equal to 4 times F divided by tau, which is 37.5 megapascals, times pi 3.142 times the diameter squared. So you plug all of the numbers that you know into the formula. So it's 4 times 12 kilonewtons, 12 times 10 to the power of 3, divided by 37.5 times 10 to the power of 6, that's the 37.5 megapascals, times pi 3.142, times 6 times 10 to the minus 3 squared. That's the diameter of the rivets. Okay, and when you do all that, you put all that into your calculator, you will get number of rivets is 11.3. So we take it up to the next whole number, not down, up to the next whole number, and we would use 12 rivets in this particular instance.